Hi everyone, and welcome back to another STK based tutorial. Today I want to introduce some changes that have happened with stko, so a Python package that uses, optimizes, calculates properties of STK molecules. So I'm going to run through the documentation a bit. The main thing is that we've updated the stko documentation, and we've started requiring Python 3.11 for stko. So I'll show you the installation of that in a second. But the main thing is, for anyone who was already using stko, the existing functions or interfaces or classes that you were using were the same. So if you were importing stko and running stko.uff or stko.xtb, those will be the same. However, as we'll show in the documentation, the new documentation is now much more organized, and we can see the different molecular calculator optimizer classes on the left. But what we are doing is we are putting any new functionality in specific modules. And what I want to talk about today are the new functions in the molecule analysis module, which include ways to analyze cages. And I'm going to go through an example of this, but you can see there's quite a few useful things here to analyze the geometry, the pore, or particular subgroups. So looking at how planar benzene rings are, this C6 planarity function we use, or you can decompose metal organic cages as well, for example, using this class. And so each of these will have an example of how to use them. If we go to the examples page, or in particular the cage analysis example page, what I've done here is I've taken a lot of the code I've used in published papers where we're looking specifically at palladium cages with ditopic ligands that interact through pyridal donors. So these groups can be represented by what I've now introduced as a three-site functional group, which we can define through a three-site factory. In particular, the CNC factory looks for a carbon connected to a nitrogen with two bonded groups and another carbon. So all of this comes together and really simplifies the analysis of these workflows and generalizes the workflows I'd used in the previous works. So that was the main thing. I want to run through this example that I have written. It will be as part of this page, and it's also available in the examples folder, so you can go to cage analysis example.py, and we're going to just run through some steps of it. It's not exactly the same, but it should show the overall summary. So I obviously have written it before. So we have a palladium atom and a ditopic building block, which I will just show looks like this, and we can build a cage from that, an M6L12 cube from that in the normal way, using MC hammer to produce this optimized loosely structure. And you can see it's got 12 of these organic linkers and 6 palladium atoms. So once we've built the cage up until this point, we can use the decompose mock class. And what this does is it takes all, it specifically mocks for metal organic cages because it's about disconnecting metal atoms and taking only the organic components. So we can run this whole thing. Oh, sorry, first I need to create a Python 11 environment. So mumba create stk examples Python equals 3.11. And so mumba is a more efficient version of conda, which I've started using, and it makes this whole installation process much quicker from my experience. So once we have installed this, we can then move to that environment, and we can go pip install stko. And so this should now install the latest form of stko, which the versions of stko now have dates attached to them. They're no longer a version 1.00 format. They are now, where is the actual version number? It should be 2023 November sometime. There you go, stko 2023 11.13. So this is much more in line with the STK format. So once we have that, we can now go python gist.py, the name of the script. So it's going to build the cage, and then we're going to see that there are 12 ligands. So this decompose mock will take every element with an atomic number of 46, so palladium, and it will return a series of ligands. And so we can see that here, if we take the original cage, we can overlap the original ligands like so. Now they're all colored differently, and they're all different molecules, which we can analyze differently. So we can look at their strain energies, or we can look at their geometrical properties. And so that's exactly what we do in this for loop here, where we use the ditopic 3-site analyzer. So this is for molecules with 2 3-site functional groups, which is exactly what we have with this ditopic building block. Again, there's carbon, nitrogen, carbon, and there's 2 of those. And so I've implemented this ditopic 3-site analyzer, which has some methods specific for these cases. And some of these are looking at the angle that the nitrogens will make with palladium, or the angle that between the 2 nitrogens, or the distance between nitrogens, or even the torsion between those nitrogens. So it's just looking at the relative geometry of the binding sites. And so if we press enter, we can see that we take this 3-site analyzer and we run, for example, we apply to each ligand, we apply the 3-site factory, looking for carbon, nitrogen, carbon. And we can then do 3-site analyzer.get binder distance, or get binder angle. And hopefully each of these methods will have a good explanation of what the geometrical property is. And then we have just printed out here the average for all of the ligands in the cage. And this can be quite useful when you have when you're trying to analyze the strain in a system, for example. The next thing we can do, which I'm not going to show any output of, but we have decompose mock, which will take metal atoms, delete them, and give you distinct molecules. Whereas constructed analyzer, it implements 2 methods for extracting the building block centroids. So each time you place a building block, either a palladium or a ditopic ligand in this case, you can potentially follow the position of that building block as the cage is optimized, for example. And this is actually similar to what we use for topology extraction. And then the next thing we do is we've introduced the geometry analyzer. And this can measure things like the minimum distance between the center of the cage to an atom. So it's effectively the pore size, or we can look at the average cage size. So this is the average distance between the center of the cage and all of the atoms. And a large standard deviation, which is the second number, would suggest the cage is very flexible or collapsed even. And then we also have things like the metal distance or metal centroid angles. And these are just averages here, but you can imagine extracting individual ones that are of interest to you in your analysis. And then the geometry analyzer also, so this one here also contains measures for the ability to calculate bond lengths and bond angles and so forth as well. And these are returned as a dictionary of tuples for the particular interaction. So nitrogen-palladium bonds, if we click enter, we can see the average nitrogen-palladium bond length is 2.05 angstroms, which is what we would expect, even though we've just run MC Hammer. I think we got lucky there. And then nitrogen palladium angles. They are either, it's a square planar configuration, so you have either the 180 degree angle crossing trans to each other, or the 90 degree angle cis to each other. Yeah, so that's the latest additions to stko. Obviously, all of these will be available as examples. And if you have any issues, please submit an issue to GitHub. Thank you very much.